Okay, so hi all, and welcome to this penultimate, I think, next to last video on for Laplace transforms and all these guys. I will finish up with the problem that I think I left off at the end of the last video, and then I really just have a series of other examples I'm going to do and interpret results and all that other good stuff. So it's going to just do one more large video, but I think I'll break it up so that it's not a big, huge hour-and-a-half kind of thing. So we'll see how far we get, or how long it takes to do these couple examples today, and push the rest to just one last video for Friday. So we did this problem at the end of the last video, so I'll just very quickly remind you that we've revisited, I guess, the spring problem. Not to say that we couldn't have done this, what you see on the screen here, when we did the springs originally, but number one, I think there was plenty there. I don't think you needed even more problems to worry about. So that's one reason. But the other reason is just that, these, what did we add to this? We added to our spring model the possibility of what we've been calling, or what we're calling, an external force, right? Which is just a fancy word for a force that is not built into, I guess, or innate to the system. So it's not gravity, and it's not drag, and it's not spring, or not due to the spring. It's something else, right? Anything else, whatever else you got. That if you call that f of t, again, f of t makes sense because it could change over time. Although most of the ones we're looking at are either a quick hit or a constant, but in theory it could if you had to. And so how does that modify the model? Well, here's our Newton's F equals mass times acceleration. It just adds one more force, f of t, this external force. Now the other characters still can move over to the right side like we did when we derived this model in the first place, so you still get the usual characters, m, u double prime, gamma u prime, and ku, where those things still mean the same thing that they meant before. But what's left on the left side, or if I was to write this the other way around on the right side, would be now that you have something. You have f of t, whatever that is, on the other side. So you don't have zero. So that's what makes this a non-homogeneous ODE, which if f of t turned out to be sine or cosine or a constant or any of the normal characters, we already knew how to solve this. But since we've gone through this trouble of introducing these two new mechanisms, or two new modeling things, the impulse function and the step functions, those could also end up as f of t's. And in fact, in real life, those often are the f of t's that we actually care about more than traditional math nice functions. So it's important for us to be able to revisit this model, and since the step function and the impulse function are almost like made for physics kinds of problems, it makes sense that we would throw them in as f of t's and see what it does to our familiar model. So we did one when we finished when I finished the last video. I just did a basic spring here. There's no damping, so of course we know that means motion will continue forever because nothing is there to slow it down. What did we do here? We said, so let's take the spring, and then the f of t, the external force that we're going to do was just a simple step function. So it's 0 up until time 4, and then it's 2 after 4, which of course just means you're constantly giving it a force of 2, whatever units are, forever. So of course, there's two reasons why this is going to be in motion forever. Number one, you have no damping, so there's nothing to slow it down. There's no u prime term. But also, you're giving it force forever, which means unless you happen to be doing that in some sort of an equilibrium kind of a thing, which we know is not true, because equilibrium is established from the elongation. So we know that there's two reasons, really, why this one's going to go on forever. We'll look at some variations of this where I isolate the one or the other. But we solved it, right? And this was not too bad to solve with our newfound tricks. We used Rule 10, which is pretty much the rule we're going to use every time we have an E which of course the E comes up anytime you have a step function or a impulse function. You're going to have e's in your transforms. So you're pretty much going to be using rule 10 unless you happen to get lucky and it's rule 9. But for the most part, we're going to be using 10, which just really essentially requires us to solve a regular problem and then shift the answer. So I'll keep sort of reminding you to be cautious of the shift. It's not hard, but you just have to remember. And so we ended up with this as, this as our solution in the box here. Okay, now of course I'm going to pull this apart a little bit, so I'm just going to get a clean slide. So just keep going here. So our solution, okay, so our solution U, which of course is displacement as it always is, turned out to be this. So I got 2U4, and then 1 minus cosine of that's 2 minus 4. Okay. So what is this, right? Or what does this look like? What is this really in real life? So there's a variety of ways for us to kind of imagine what this is. I'm going to just give it to you in a couple of interpretive ways, I guess. I'm going to draw a graph in a second. But since this is a step function, U4, so, you know, I mean, you could leave it like that and expect the user or the reader to know what that means, or you could do them a little bit of a favor here and sort of do a little bit of interpretation, where you say, well, the step function, you know what that does. That does something that's either 0 or 1. So up to time 4 versus after time 4, you have two very different behaviors. Now up to time 4, this is 0, which of course is going to clear out this whole thing, which means your solution is just 0 up to time 4. And then after time 4, this is just 1, so you don't really need it. So then what do you have? You have 2 times 1 minus cosine of t minus 4. Out of space there. Okay, so, right, so this is probably a little more user-friendly to say that, not that you have to, but just to get wrap our heads around this, it says, oh, okay, so remember, U is displacement. So there's no displacement, in other words, there's no movement for time up to 4, up to time 4, and then at 4, this is going to govern movement for the rest of time, really. So if I wanted to graph these, or graph this, I should say, I could. If I need to, I can say, all right, so at time 4 is kind of where there's a change in behavior, so I'm at least going to put time 4 on the graph. And then, probably the piecewise function here is the best way to look at this. So, this is 0 up to time 4. Oh, okay, so U of t, that means I'll do it in a different color here. The solution is 0 up to time 4. And then after time 4, it does this. You can punch this into your calculator if you want. It's a cosine graph. And the fact that it's 1 minus basically just means it's an upside down cosine graph for all intents and purposes, I guess. The fact that it's the fact that it's minus means it's upside down. The fact that it's 1 minus means it's moved up 1. So rather than oscillating between -1 and 1, this will oscillate between 0 and 2. And then I'm doubling it, which I'm pretty sure means it'll oscillate between 0 and 4. So I'll put 4 up here. So punch this in if you're not great at sort of sketching this by hand. Just type that into your calculator. Now you don't have to worry about the whole, it only exists after time 4. Just zoom over on your graph till after time 4, right? This one, you could fill this piece in just by thinking, and then just pick up with this graph at time 4. Or you could move the window over to only start it at time 4 if that makes it easier. So I think if you graph this, let me see if I get this right. I go up first, I think. Cosine of 0 is 1, so that's 0. And okay, yes, I do. I go up first. Okay. So I get a cosine graph, and you don't have to be fancy about drawing this with any sort of precision because all cosine and sine graphs just look the same. So you get something like that, right? If you want something a little more official, you could always sort of more cleverly or more honestly graph it, but basically you get that general shape. So let's make a little bit of sense of what this is and what this means and all of that. So of course it makes sense to say that after time 4 is the only time that you actually have any sort of motion. So let me write down some notes here. Sorry, I'm just graphing this myself just to make sure I'm not... what does that look like? All right. Okay, yeah, I'm right. Okay, it goes up first. Sorry, I just wanted to make sure I wasn't telling you a story here that wasn't true. So some notes on this. Some comments, I guess. So of course we can see there is no motion up to time 4. And let's see, does that make sense? So let me go back to the problem. So this is so what does our ODE say? Well, our ODE says, okay, we have our spring stuff here. This doesn't start until time 4. But of course, these guys over here, which we used in our solution, that's where these zeros came from, it hopefully makes sense that since I'm not giving it any initial displacement, and I'm not giving it any initial velocity, the spring is just sitting there. And this doesn't turn on, this external force doesn't turn on until time 4. So of course, hopefully this makes sense that there shouldn't be any motion, right? There's no motion up to time 4 since there is nothing to set it in motion. Right? I mean, this should make sense with reality. If you have a spring that's at equilibrium and you start your timer, but you don't do anything to the spring, well, it's not going to magically just start moving. Even it's just because you started the timer at time 0 and say, okay, go. But what happens at time 4 minutes or seconds or whatever is you turn this fan on or whatever, this thing that's extruding a force onto the spring, which causes it to start moving. Okay, and of course it's a positive force. We chose it to be a positive 2, right? I think that's what we did, right? Oops. 2, right? So it's a force of size 2, positive 2, which of course means you should be moved in the positive direction, which of course in real life is downwards movement. Remember, up positive is down. So this force of 2 that's being pushed is actually a downward force, and that makes sense. So the spring moves down. Again, remember that's actually a downward movement, even though it's positive on my graph here, but that sets it in motion. All right. Now, of course, there are other things to say about this, so that makes sense about the whole starting thing. Now, what else? So we notice if you graph this, and even just looking at this is never going to get bigger or smaller because cosine just does its thing, and these are just some numbers surrounding it. So I have no E piece to this. That's what usually either makes the oscillation grow or shrink. Well, in this case, I don't have that, so the oscillation is just going to be continuous. In other words, this is the graph forever. So, of course, we also notice the oscillation continues forever. And this is, in this case, because of two things. One, you have no damping. So that was actually sort of I'll do one that has damping so that you can see what happens. But as soon as you have no damping, the movement is by default going to always continue forever because there's no resistance to slow it down. But also, you are giving it a force of 2 forever. Right? That's what our step function was at the beginning of the problem, the f of t. the external force, that doesn't shut off. So you have this fan that you turn on, but you leave it on. Oh, right. So of course it's still going to blow this spring and cause it to keep bouncing. So even if there was damping, the fan would keep it in motion forever. Okay? So, so this isn't surprising that we ended up with this kind of a graph or this kind of a solution. This is hopefully matches our intuition of what should happen if we were to actually do this thing. Okay, so that's nice. So that's practice with one that uses a step, right? So in this case, the external force was given to us in a step function format. So let's try one that does a impulse, and then we'll actually modify that one a couple times. So I'll call that example 1 that we just did. So let's try 2. So suppose that we have a spring followed by, and once again, obviously this could be given to you in words with the usual setup, but we'll just cut right to the ODE so we don't have to wade through all of that stuff. Okay. Okay, so here's our ODE. So let's make a little bit of sense of it before we jump into solving it. One thing we might notice is that there is damping here. So that means we do have resistance. So that means that the spring action, the oscillation, should eventually slow down, or come head towards 0, assuming that there's no continuous force acting on it, which I think we'll see that in a second is true. So there is damping here, so we do expect more of a that sort of situation, but well, we'll see. What's this? So this is the delta function, or the impulse function here. Remember, this means an impulse, and in this case it's at time 5. Now there's a 12 in front of it, or I put a 12 in front of it, just to indicate that the size of the force, or the total amount of force that you give it at time 5, rather than just being 1, is 12. Okay, so this just means instead of it being a light punch, it's a hard punch, right? Or a flick, probably, since this is a spring. All right, so of course this means we impart a force of size 12 at time 5. Now, of course, that's an impulse, so that means it's not like the light switch that we did in the last example. This was a force of size 2 that started at time 4, but went on forever. But remember, an impulse is just what the name suggests. It's a quick hit, so it's at time 5 and then it's off. That's it. So this is quite literally, right, a punch or a flick, as opposed to a fan or some other thing that can impart a constant force for a duration of time. This is just a quick hit. Okay, and the usual, just to emphasize what's happening here, is that there's no starting movement, or whatever you want to call that, right? I'm not giving it any initial displacement, and so I'm not pulling the spring down or compressing the spring up, and I'm also not giving it any initial velocity, so I'm not giving it a hit when it starts. So just like we did in the last example, so that we can hopefully see this emerging, we will give it no initial starting motivation, and instead we'll wait until this, which in this case is a flick, a punch at time 5, that's what's going to set it in motion. Probably. Well, hopefully we see that in our solution. Okay, so let's solve this. This will give us a little bit of extra practice using Laplace and all of our strategies and all that good stuff too. So let's solve this. So so we'll solve this. So I get 2. I have a 2 in front of this, right? So I have 2 s squared Laplace of y minus, okay, I still have my 0 and 0 because these are both 0. Okay. And then 8 the Laplace of, oh, I'm sorry, I'm so used to writing Laplace of y. We're doing u now, so Laplace of u. 8 times u prime, so I get 8. Remember, the Laplace of u prime, or y prime, is s times Laplace of u, minus 0, again, because the u of 0 is 0, so that's nice. And then I have 26 Laplace of u's. Now on the right-hand side, I have to do the Laplace of this, this stuff. Well, a coefficient is no problem. That just comes along, so I get 12. And the Laplace of the delta function, or the impulse function, that's rule number 11, I think. It gives us just an easy transform, e to the negative 5s. Okay, so there I'm done. I'm done with the step 1 of solving. I transformed everything. So now, as usual, let me make this read Laplace of y equals, so that I can organize my, my thoughts here. So I'm just going to do this all at once. So if I factor out a Laplace of u, that means I have 3 terms. And if I factor those out and divide them to the other side, I think I end up with Laplace of u equals. And when I move those guys to the other side, so I have 12 e to the, I don't know why that looks weird, 12 e to the negative 5s. And it's really divided by these guys. But since I'm probably moving towards rule 10, because remember rule 10 is pretty much how we're going to deal with any time I'm going to have e in order to go backwards. How about I do it this way instead, just to sort of move us already in the right direction. I'll just write it as 1 over, and then of course the s stuff that I have is that. Okay, so I did a couple steps in one there, but it's all just algebra. So, all right, so I end up here. So I have Laplace of u equals that stuff. And again, I'm mostly thinking, oh, with the e thing there and with some s stuff over here, that's kind of nice because it'll make it look like rule 10. And rule 10 says, of course, that I take the f of s, right? So in thinking about rule 10, in a moment, I'm going to hopefully be able to write down u equals, or u of t, equals, right? That'll be the inverse of that. I'm pretty sure I'm going to get a 12 here. And the e will turn into, so that tells me c is 5. And I think I'm going to use rule 10. And that's going to turn into a step at 5. So u5. Okay, but to make the rest of this work, I actually have to do something. So this piece here, so I'm going to call this piece big F of s. And now rule 10 says if I want to go backwards, I need little f of t minus c, which for us is 5. Oh, okay, so I got to pause for a minute. I'm not ready to do that yet. So let me come over here and do a little side problem. So I'm going to just sort of strip this away and say, okay, so my challenge for the next few minutes is to figure out what to do about this. Okay, that's big F of s if I'm trying to use rule 10, which I am. So I need to come up with little f of t, because ultimately I'd like to come up with little f of t minus c, or t minus 5 in this case. Now, as long as I can get little f of t, plugging in t minus 5 is just a simple substitution, so that's no big deal. But I do need to figure out little f of t, which of course is the inverse transform of big F of s. So here's my big F. I need to know what little f goes with this big F. Well, this is just a standard question now, a standard use the chart to do an inverse in order to get the inverse of this thing. So if I'm looking at this, I'm doing my usual tricks by now, which hopefully you're getting comfortable with the chart, which is I'm saying, oh, hey, this would be nice if it was in the right column of my chart somewhere. And remember, I'm mostly looking at the denominator of the fraction and hoping that that's there. And then thinking back to the stuff from last week, I look at the bottom and I think about, oh, okay, if that factored, I'd probably want to factor it and do partial fractions. If it doesn't factor, I'd probably want to do a complete the square situation. So I'm not super excited about this 2, and none of us are, because it always makes it a little trickier to do any sort of factoring or algebra. So just factor that 2 out. I'll just do it over here, I guess. Well, maybe I'll come below here. So if I factor that 2 out, that becomes a 1/2 in the bottom. or becomes a 1/2, I should say, because the 2 is in the bottom. So I at least have a little bit of a nicer thing to look at. But now at least I can see very clearly that this doesn't factor. If you try, there's only 2 numbers that multiply to 13, 1 and 13, and I'm not going to get a 4 out of that. Okay, so this is our trigger to say I got to complete the square. So I'm doing a side problem to my side problem at this point now, I guess. Don't want to get too carried away here with this stuff, but so I think I need to complete the square on this guy. And so just remind yourself that means I'm trying to make it look like 1 minus a squared plus b squared, because I'm trying to use rules 6 and 7. Okay, so for this I just have to think for a second. S and 13, and then this of course would turn into s squared minus 2as plus a squared plus b squared. And then I just look for a second and use basic logic here to say, well, those have to line up, which means, right, so 4 has to equal negative 2a, which of course tells me a is negative 2. And then the other 2 pieces have to line up also. So 13 has to match a squared plus b squared. Well, a is negative 2, so that would be 4. And so I can get that 9 is b squared, or 3 is b. So whichever of those is more useful to us. Okay, so let's see. Let me start to move from right to left now, since we're ready to finish this thing. So so we completed the square, which is just an algebra trick. So this expression here can now be written like this. So let me do that. So that's 1/2 1 over. So s squared turns out to be s plus 2, because it's s minus a, but a is negative 2. So s plus 2 plus 9, also known as b squared. Right, so that's me just filling this in. And now this looks almost just like rule number 6, I think. 6, maybe, in the chart. Yeah, 6. Except for rule number 6, you need a b on top. So this is the only place where you have to do a little bit of thinking here, or a little more thinking, I guess. This is b squared, 9, which of course means that b is really 3. So the fact that I need a 3 up here, which you need to triple this. So if I multiply by 3 on top to make a 3 appear here, I can just offset that by also dividing by 3. So I think I can get away with doing 1/6. 3. Now I have a 3 on top, which I need. 3 over this stuff. Okay, so that's big F of s. And so I'm ready for little f of t. This is using the chart. This is number 6 on the chart. So I get 1/6. I'm running out of space here, but I'm going to cram it in anyway. So if I look at rule number 6, I get e to the a t sine of b t. Okay, so I end up with that as my little f of t, which is good, because now I'm going to take this, and to complete my original problem, which of course is what I wanted to do here, rule 10, which I had put on pause for a minute to go do these side problems, said if this is big F of s, then you need to write down little f of t minus c, which is what I'm about to write down. I have little f of t, and so the only difference between little f of t and little f of t minus 5 is that I'm just going to replace my t's with t minus 5s. Okay, so I'm going to write down my final answer here. So 1/6 e to the negative 2 t minus 5 sine of 3 t minus 5. And that's my answer. Except I am going to do a little bit of neatening on the next slide here, but that's all right. You can put a box around that if you want. Okay, So it's a little jumbled here. Sorry, I didn't leave myself quite enough space, but those should be all the steps. So this is good. Again, good practice doing the Laplace stuff. And then now let's process what the heck is this that I boxed over here in the corner as my answer. Hopefully it agrees with our little preview of the discussion, preview of what the answer should be, and hopefully this is agrees with that idea. So let's see. So what do I have to? So let me make a little bit of sense of this. So first of all, I have 12 here, and I have 1/6 here. So that's a little silly. Everything is multiplied here. So I should probably just write that as 2. Right? So I'm going to put the 12 and the 1/6 together and call that 2. So when I copy this over on the next slide, how about I go with 2? Okay, and then I have U5. Okay, so I got 2 U5, and then I have this stuff, the E and the sine thing. So I'll just write that down. Sine of 3 t minus 5. Okay, did I do that right? Oh, I missed a 2, did I? Negative 2 t minus 5. Okay, so that's my solution. You can distribute this if it's helpful or if you want to. A lot of times people leave that in just so that it draws the users or draws the reader's attention to the fact that this is just a shifted E and a shifted sign. So sort of stylistically, you usually just leave the t minus 5 rather than distributing this. But if you're graphing this, you could certainly type in 3t minus 15 if you'd rather do that or something like that. It's fine. Okay, and of course, I could write this piecewise, maybe just in the interest of saving space, I won't do that, but of course, we know what this means. The step function is the on-off switch, and up to time 5, this is a 0. So if I'm going to graph this, let me go right to the graph. Okay. So up to time 5, put 5 about there. I know that this is 0. Now we haven't looked at an example yet where we have, we're going to do some in the next video, where we have sort of a part 1 and part 2. So I don't want to say you always get 0 up to the step, because it's possible that we give it some motion in order to begin the problem. But for this, in this case, right, when you just have a single term and it's got a step function multiplied by it, then yes, sure, right, that's off up until time 5, or 0 up until time 5, so of course, right, okay. So if I graph this, come here, blue again, it's not doing anything for the first 5 minutes or seconds or whatever. And then after that I have, this becomes a 1, and so I just have this stuff. Right, so that's 2 e to the, and so what's happening to this, right, even before I sketch the graph here, as time gets bigger, so as t goes on here, sine just does its thing, right? Sine's just a wiggle, right? So sine is, of course, just trying to do that forever, and it does. But now what's different about this one and the last problem is that you have an e piece, and in particular, the a up here is negative. So as t gets bigger, we know that that exponent up there on the e, we know that that's getting bigger but negative. So that means that the exponent is becoming a large negative number, and we know that that means that the whole thing is going to 0, right? E to the large negative is heading towards 0. Oh, okay, and the fact that you're doubling it, who cares? And sine just keeps doing a wiggle, doesn't actually contribute any sort of amplitude to this. It just says, hey, I wander between -1 and 1 forever. So this is going to end up being similar to the last one. However, a big difference is that this is going to have that. Oh boy, sorry. First part of that was pretty good, but okay, this is going to have a diminishing, right, or vanishing oscillation because of the E piece. All right, so I promise if you punch this in your calculator, again, leave this off, leave the U off. You don't have a U function in your calculator. But remember, that's just 1. So if you graph 2 times this stuff, and just look at the graph from 5 on, I promise it looks exactly like this. Okay, so I think this gets close to 1. I think it stays a little bit under 1 when I graphed it. So the maximum here is a little bit less than 1. But so let's say some things, as usual, some notes or some thoughts on this. So just like we said before, or we saw before, there's no motion. Up to time 5. And again, that's because there's no initial force. Right? There's no initial displacement, there's no initial velocity. So of course, this is going to just sit there because you're not doing anything for the first 5 seconds, or whatever units we've got. Right? So this is just sitting there. Okay, great. Now at time 5, I give this a big flick, a force of positive 12, which of course is really downward. But on our U graph, that's going to thrust the displacement in a positive direction, which is actually down. But it should make U positive initially. But this is just a flick. This is a quick hit. So of course what happens is that since we have damping here, damping the air resistance, even though I give it a nice whack in a downward direction, it boings for a little bit, but the air resistance here is slowing it, is going to eventually slow it down. In fact, 8 is a pretty big number, so it actually has quite a bit of drag. So I don't know what object we've put on the end of this thing, but maybe it's something that's not terribly aerodynamic, and that the air resistance imparts a huge drag force that slows it down rather quickly. All right, so and we see that in our graph. So now, of course, at time 5, we give it a positive, which is actually a downward flick, I guess I'll say, which sets it into motion. So setting it into motion, which we see. But the damping slows the oscillation down to 0. And in this case, it does so rather quickly. Okay, so that makes sense, right? And this is, again, the damping, with damping present, is more of a real-life example of spring motion, right? Because in real life, you have air resistance, unless we're on the moon or something. So of course this makes sense, right? This is us now. This is us saying, we got this little spring set up, we called our friends over, and we hyped it up for about 5 seconds, where we told them, look at what great stuff's going to happen, and you talked for 5 seconds while nothing happened. And then at time 5, you gave it a flick, and it did some bouncing, and then because there's resistance, there's drag, it eventually settled down back to equilibrium. Right? So probably of all the spring problems that we've probably done dozens at this point between class and homework. This is probably the one that is us for the most part, right? More so than anything else. Maybe we do the pull it down to start with and let it boing up. That's probably a good one too. We like that, but this is pretty accurate, and I think this matches our intuition about what should certainly be happening. Okay, so that's a good example too. So we've now done one of each where we have nothing, no starting movement or no starting motion, and we tried one that has a simple step and one that has a simple impulse function. Other variations that we'll try is, what if we do give this some initial, so in fact I'm going to redo this problem, but rather than having these both be 0, let's give it some initial velocity, for example. So that means that motion is actually starting at time 0, because if I give it an initial flick, then I shouldn't see this big 0 period. I should also see some bouncing over here, so we'll do an example of that. And then we'll also do an example of when we maybe use the step function, since that provides continuous force. So if we took maybe the step function from the first example instead of an impulse, but we have damping, that's sort of a good battle there of damping is trying to slow the motion down. Or damping tries to kill the motion or have it go back to equilibrium. But if you have a force that goes on forever, it's constantly perturbing it. So that'll be an interesting one. That'll be our last example that we do to kind of wrap it up. So we'll do both of those examples in the next video. So this, I think, is a little bit of a shorter one, which is fine because I think the one from Monday was a little on the longer side. So we'll do those last two examples. You're well equipped at this point. I don't think the book, the homework problems have anything more complicated than the one we just did. In fact, they don't really use the step function quite as much as the impulse anyway. So you should be all good to go to do all the homework at this point. It's due on Monday, so do check it out. There's a significant number of problems, so give yourself a healthy amount of time to start on those in case you have questions or get stuck. You can get some help. And I will talk to you on Friday.